Now we come to question 2, which is the first of 2 multi-part questions, which involve a variety of different integrals. And Math 1001 exams will sometimes organize these kinds of questions in several ways. So for example, sometimes you might get an exam where one question is all about integrals where the technique is specified for you, and then there's a second question which has a bunch of integrals where you're left to your own devices to figure out the appropriate method. Sometimes you'll see exams where the integrals are split up by the types of functions involved, maybe integrals of algebraic functions in one question, integrals of transcendental functions, so trigonometry, logarithms, things of that nature, in a second question. In this case, certainly based on the number of marks assigned to each of the integrals, what seems to be happening here is that we have slightly simpler techniques in question 2 and slightly more advanced and sophisticated techniques in question 3, but let's go through and let's see if that actually bears out. So the first one that we're going to deal with here in question 2a is a definite integral, although that doesn't really impact our choice of technique. And so for 2a, we're being asked to evaluate the integral from 1 to 4 of the function 1 divided by the square root of x times 1 plus 3 root x all squared. And so like I said in the preamble, when it comes to choosing an integration technique, it's always worth starting with the simplest possibilities. Now, is this an elementary integral? Definitely not. And of course, we have to bear in mind that when we've got a quotient, there is no quotient rule for integrals. In particular, we can't simply integrate the numerator, integrate the denominator, and be done with it. It would be lovely if it worked that way, but it doesn't. And nor does there seem to be any way to rewrite this so that it does become a sum or a difference of elementary integrals. So what about u-substitution? Well, there's a few things that we often look for u-substitution. We frequently look for composite functions, functions inside other functions, which we've got here. The 1 plus 3 root x is inside the power of 2. And perhaps more importantly, we're looking for expressions whose derivative, maybe without a constant multiple, is also present in the integral. And that's also true in this case, because the derivative of 1 plus 3 root x, well, of course, the 1 is a constant term. It differentiates away to 0. So the derivative of 3 root x is a multiple of 1 over root x, which is exactly what we've got there. So yeah, this does really seem like a u-substitution question. So if we let u be 1 plus 3 root x, then du, the derivative of that expression, would be 3 times the derivative of root x. So that's a half times x to the negative a half. Then, of course, times the differential dx. So that gives us a constant of 3 over 2 here, which isn't present in the integral, but that's fine. We know how to deal with that. We'll divide it across to the left-hand side, and that tells us that 2/3 du is equal to x to the negative a half, or 1 over root x times dx. But we're not quite done with our setup for the u-substitution yet, because this is a definite integral, which means that we also have to transform those bounds from the x values, which is how they're given to us, that's x equals 1 and x equals 4. We have to figure out the corresponding values of u, but we do that simply by substituting into our expression for u. So in other words, when x is equal to 1, u is going to be 1 plus 3 times the square root of 1, which is simply 1 plus 3, which is 4. And likewise, when x is 4, u is going to be 1 plus 3 times the square root of 4. That's 1 plus 6, which is 7. So in this case, then, the integral becomes, well, what was the integral from 1 to 4 of 1 over root x times 1 plus 3 root x all squared. That's now going to be the 2/3 from our u-substitution, from the differential, times the integral, now from 4 to 7 And our integrand, well, the 1 plus 3 root x in the denominator just gets replaced with u. So that'll be a u squared in the denominator. And the 1 over root x times dx all becomes the du. So we've just got 1 over u squared, or u to the negative 2, times du, which is now a very nice, straightforward elementary integral. We apply our power rule for integrals here. So that's going to be, add 1 to the power is u to the negative 1, divided by the new power of negative 1, and we're going to go from 4 to 7. And remember, the trade-off for that work of transforming the bounds at the start of the problem means that in this case, because this is a definite integral, we don't need to switch back to the original variable x now that we've evaluated the integral. We can just plug in u equals 7 and u equals 4, and the fundamental theorem of calculus applies just as well in terms of the new variable u as it would if we switched everything back into terms of x's. So in other words, if we pull that negative out, we'll get negative 2/3 times 7 to the power of negative 1, or 1 over 7, minus 4 to the negative 1, which is a quarter. We can find the common denominator there. So 1 over 7 is 4 over 28, minus a quarter would be 7 over 28. So that's minus 3 over 28. Cancels the minus 3 that's already outside here, leaving us with 2 over 28, or 1 over 14. There's that first integral done. We'll move on to part B in the next video.